So it's been a while since I've done a project video or like a full design from start to finish. So I figured now that it's been years, it seems like, since the Raspberry Pi microcontroller, the 2040, has been out. And everyone who's going to make a video on it pretty much already has. I figured I would throw my hat in the ring and do one myself. So, and I actually have the board already done and finished. So this project actually will be completed, unlike a lot of my others. But it's basically just going to be a simple evaluation board, nothing too special, just with an I2C interface and a USB-C input. I am going to do a couple things that you don't see a lot of times in hobby level or on like YouTube tutorial videos, and that is it's going to be a 4-layer board, and instead of just using a crystal for the microcontroller's clock, I'm going to use a powered oscillator. And I'll explain kind of the thinking behind that when we get into the video more. But with that all said, let's jump into it. So with this project, like a lot of the other ones you've seen me in the past do, is I'm going to start with a hierarchical sheet. So for this, I'm just going to name it RP2040 because this is going to hold the main microcontroller and all its peripherals. And of course, once we get all of the pins and everything, I can adjust the size of it. But for now, just do something by default like that. And I'm not going to show in this video how I build these symbols. What I'm going to do is for the Patreon patron supporters, I'll throw it in the supplemental video for this, but it's pretty straightforward, obviously. And I always like to start with the power connections on pretty much any, whether it's routing a board, the PCB, or starting the schematic. So this part's kind of weird in that it doesn't have separate ground pins. It just has its single exposed internal thermal pad, and then this test enables just a internal Raspberry Pi pin that they say to connect to the ground also. So the power scheme for the RP2040 is a little interesting. It takes in a single 3v3 power rail, and then it also needs a separate 1v1 rail. And for the 1v1 rail, it's actually able to be generated internally from the VREG out pin, and that is from the VREG in from the 3v3 rail. So it takes 3v3 from here, drops it down to 1v1, and then outputs it to the two DV-DD pins. Since the 3v3 rail is going to be something that is from the outside of this sheet, I will make a 3v3 hierarchical sheet label for it, or 3v3 hierarchical pin. And so this will be on the outside of the hierarchical sheet, saying we need to have 3.3 volts input. And then for the decoupling capacitors, for this project, I'm going to do it in all 0402s. And that's just to kind of keep the size down. If you're working on a similar project like this or you're copying this, by all means, obviously, you can use 0603s, 805s, 1206s, whatever you want to do. But I will keep using just the 0402s. And I know these aren't all going to fit, but since we have 1, 2, 3, 4, 5, 6, 7, 8, 9, I'm going to just go ahead and do 9 decoupling caps. And then when we start doing the PCB, I'll just delete the excess. Another thing you've probably heard me talk about or seen in the past, I always like to over-design things at the start, and then when the board is actually finished, if I need to drop down the BOM count for cost or any other reason, I'll do it then rather than have to do it the other way around, because that is obviously a whole lot less fun. And now the 1v1 rail is only used on this sheet. So I'm just going to give it a 1v1 label. I don't have to do that, but I find it sometimes makes it a little bit easier doing the PCB layout because I know what that actually is instead of having to keep referencing the schematic. And for this, again, since there's 3 pins here, I will do 3 capacitors, and you certainly don't have to do this many either way. Even if they do all fit, I'm sure you could get away with just a couple on each side. But I will have a bunch, and then we can drop it down. So I have the input supply. So again, 3v3 comes in. You got decoupling caps here. It supplies power to the internal rails. And this ADC AVDD, you could obviously throw like an LC filter or some other analog supply on here. But as far as I've gathered, Raspberry Pi, these microcontrollers aren't that great on the analog side to begin with. And for this evaluation board, I honestly don't care too much about analog performance anyway. So that's why they're all tied together. But if you do want to use this more for analog, you would supply this pin either separately or at least just from some sort of filter. So now from here, another place I'll like to go is on the reset circuitry. I don't know why the Raspberry Pi, I keep saying the Raspberry Pi just because that's the brand. I need to just refer to it as the 2040. The 2040 uses the run pin for the reset instead of just naming it reset, which is kind of annoying. So I'll label it reset from the outside, so that's all you'll see. And it's active low, like pretty much all reset pins are. So if it is held low, it will go into a power on reset mode and be held there. So I throw on, again, probably overkill for most applications, but I throw on both a capacitor and a pull-up to make sure that any glitches on here won't accidentally drop this down and reset the board, which we, of course, don't want. So with that done, the USB we don't need right now, the clock, I/O, that's for programming. Next is the X in and X out. In the past, with most tutorials you'll see something along the lines of this, where they throw on a crystal like this, and then they will throw 2 capacitors, definitely not 1 microfarad. Typically, they will be on the order of some picofarads, and then tie them to ground. And I'm not going to get into the actual inner workings of this because it's really not important for what I'm trying to go over. But basically, X out is generating an AC signal, which causes the crystal to oscillate, which then uses the calibrated, accurate pulse on the X in pin to keep track of time for the rest of the microcontroller. You need it for anything where you need more accuracy than just the internal resonator. A problem with this sometimes is you base the value of these capacitors roughly on the load capacitance of the crystal, but it's also based on the parasitics of the traces, which of course you can do some hand waving and just guess, but until you actually build out the board and then see if it works or not, you're just guessing for the most part, which is fine, and it works a lot of times. But especially for if they are like for projects that we'll do at work, if it's a expensive low bomb count or low production number board, instead of doing that, I will almost always throw in a powered oscillator. And I think for hobby boards, it also makes a lot of sense because if you're just building a handful of these, what's an extra few dollars for a oscillator? It doesn't really add anything to it in cost-wise. And what's really cool about it is internally, this basically has all of that matching circuitry, everything built into it. So literally all you have to do is apply power to it, throw a decoupling cap, and now you are pretty much guaranteed that you're going to be getting exactly your 12 megahertz signal to the XN pin. And different microcontrollers will give different guidelines for what you do with the X out in this case. The 2040 doesn't really specify, so I just throw it with a floating pin. A lot of times you will drive it low, either with a pull down or just tie it straight to ground, but just check the data sheet and see what it says. And then we also have to throw the standby, which this should have the line above it, the superscript, to show that this is also active low. But we pull it up, so now it'll always be on, and it'll always be generating that clock signal. So now from here, the next thing I want to go to is the GPIO. And since this is just an evaluation board, there will be a couple other components on here, but for the most part, they're just gonna break out to pin headers. So I am just going to take, and I'm copying this, I have these already done on another sheet just to save some time. I'm just labeling them all GPIO 0 through 23. When I use hierarchical sheets, with the exception of like here where I'm changing the name, I like to keep the name perfect with the pin on the part to what is named on the pin. So when you have it out here, without having to click in here, you can tell exactly what it's mapped to. It just makes it a little easier running through it. And I didn't do these two just because they don't fit on the number of pins on the headers I'm using. So that handles the GPIO over here. And now I will do the same thing for the GPIO on this side. Now for the USB, you can technically just take this straight out to the USB connector, but with any type of, especially USB or any type of higher speed signals, it's almost always a good idea to throw in some series resistors. And this has a lot of advantages, a lot of reasons why you do it. But if nothing else, one of the things I like to always have this for is if you need to make a modification or you need to test something, you at least have that footprint there where if you don't want to use them, you can just populate it with a 0 ohm resistor. So it's one of those things, it's like you might as well. If you don't need it, you still have it. If you need it, then it was a good thing you did. For USB, it's 27 ohm. Typically, that's what you'll use, and that's kind of a standard value for a lot of different signals like this. And what I'm going to do also is name these D minus. And I use the nomenclature N just to show like on the input side of this. And this just makes it easier for routing. It needs to have that plus or minus to show that it's a differential pair. And it just makes it a little easier to show where they actually are. So then on this side, I will name this just USB D plus. And then this will be D minus. And these, if we want to get all fancy, these are technically bidirectional. And since they're bidirectional, these resistors should go roughly halfway in between. That way it helps to slow down the rise time for both signals. Again, USB isn't that fast, so it really doesn't matter that much. And now next we have the SW clock and then the SW DIO, which is used to program without using the USB interface. So SWCLK, and then this one is an input because the computer or whatever programmer we're using will be driving that clock. And then DIO, input output, obviously is a bidirectional pin. Now the RP2040 does not have any internal flash, or at least not a large amount, so you pretty much need to have an external flash chip, and it uses QSPI, which is just quad SPI. And for the exact same reasons that I put the 27 ohm resistors up there, I will do the same thing for these pins, not the N pin, because all this is just a logic on or off. But for all of the others, I will. And then the only thing of note here, whoops, let me adjust these. So the only thing to note here is for the clock, since this is going to be generating the clock, this one we physically will want to move closer to this part, while the others, like I said here, should be at the halfway point. And again, I understand before you guys are finished typing your comment saying that I don't need this on especially the D0 through D3. I fully understand that for the same reasons I've been saying. I just like to go overkill at the start. And when I determine that, yes, we don't need those, you can just populate it with a 0 ohm resistor. So that's why for any type of signals like this, that's always kind of where I start from. So now the labels are on here. So now we have our power, we have our reset circuitry, we have our external programmer, our USB, our external flash, and then all of our I/O. So we are pretty much good to go and leave this sheet. So now at the top level sheet, what I'm going to do is just kind of adjust this more to where I think it'll end up looking. And I will import all of the pins, and I'm going to just jump through this because this is going to take a while. Okay, so now I have the hierarchical sheet pretty much set up. I'll still adjust it as we go. And the orientation and like the positioning and grouping of the I/O pins is not arbitrary. I've already checked through on the PCB and I kind of have an idea of grouping wise, so that's why they're kind of jumped around a little bit. And just a quick overview of what all is going to be on the evaluation board. So for the, and these should be separated. For the QSPI, like I said, that's going to be the flash chip. We're going to have 3v3 in, and there's going to be a USB-C connector, which goes to just an LDO, a linear regulator, to go from 5 volts down to 3.3. The reset will be just used for the programming side. The USB goes to our USB-C. The clock and I/O with the reset goes to a Tag Connect programmer if we're going to program it over that instead of USB. The GPIO 0, 1, and 2 will be for an RGB LED. 6 and 7 are not going to be used. GPIO 14 and 15 actually should be over here. And on the 2040, it's pretty flexible with its pin mapping. So I am planning on having 14 and 15 while also going to the external pins that connect to, say, the breadboard. It's also going to go to it's a Adafruit standard Stemma QT or Quick connector. So it'll allow you to interface a whole bunch of different Adafruit, and I think even SparkFun supports some of them, little I2C sensors. So I think that's a pretty useful addition. And that is pretty much the basics of it. So just to clarify, since I guess I didn't mention before, this is going to have 2 rows of pin headers that will be spaced out to be able to plug into a breadboard. So similar to how like an Arduino Nano or any of the similar type boards are. So just like with the internals, I like to start with the power supply section, but in order to have the power supply section, we have to start with the USB-C connector. So I will grab the USB, which is a standard right angle, full featured USB connector. So I know a lot of USB-Cs you can get that only have the pins for the USB 2 interface and not for the 3.0. That would totally work fine for this. You can use that. It makes soldering a little bit easier, but it's not that big of a deal to solder, so I'll just stick with this. And then I will throw on our ground here. And then for the shield, I will just leave these floating since this is going to be downstream, and there's a whole discussion on other videos if that should or should not be grounded. I will not get into that right now. So the V-bus is, of course, a 5-volt rail. So I'll add a 5-volt symbol here. And since it is our main power input, we need to put a power flag here. And while this is certainly helpful for KiCad to know and not complain in the DRC, it does not do anything to the functionality of the board. And that reminds me, we have to have one on the ground. So it simply shows KiCad, hey, input supply for this board is from here. Input supply for the ground is here. That's all it does. And then for the USB standards, you're not allowed to have anything larger than like 4.7 or 5 microfarad capacitance. So I will throw on, and I think let's go with a 4.7 mic just to have it not be derated as much for the voltage offset or the DC bias, which if you do not know what I'm talking about, you should check out one of my past videos I just did where I cover that in a whole lot of detail. And this is going to get in the way of this, so let's bump this up here and slide that over. I can't wait till KiCad 7 when they're going to have the orthogonal dragging of that, which is going to be really nice. So from here, drop it over to this side, and then for the linear regulator, there's tons, obviously, that you can use. I am going to go with this part here, which is nice simply because it's fixed at 3.3 volts. You don't have to adjust it, which would not be that big of a deal. So if you have a standard one you would like to use, you of course can. It's not going to make any difference. And input, since we have the 4.7 mic fairly close as is, I'm just going to throw one mic here and drop it to the ground and exposed pad and put our ground right like this. And now our output comes here, and we'll bump it up, and then we'll do a 4.7 mic, and this is just for a little added stability, and since we're not going to have anything quite as close there, whoops, our 3v3. And since this pin is a power output pin, we don't have to explicitly put that flag there. Since USB-C can be an input or an output, that's why we need that flag, but we don't need it here. And now I will move this and have our power go across. So 5 volts comes in. We have a couple decoupling caps. It gets dropped down to 3.3 volts with an output decoupling cap, and then it goes into our 3v3 rail, which does everything that I talked about before. Now for the reset pin, I will just throw on a reset label, which we'll use for the Tag Connect programmer. And now the USB here, all we simply need to do is add a different label for USB D plus and D minus. And keep in mind, since everything up to this point has been local labels, either hierarchical or net labels, none of them transfer out. So that's why I have to do it on both of these instead of just using that name. So now that we have these, I will take the USB, D minus and D plus. And now we have our USB, which connects the D minus and D plus, and these connect together just because the USB-C is a bidirectional, or it's a reverse polarity to where it can go on both sides. So you have to have 2 sets of each pins to handle that. And the USB 2 interface just does it dumb, where the USB 3 actually detects it. And now the CC pins, I'm not going to get into a whole lot of the USB side. I have a video on the USB hub where I talk about that more in depth. But basically, since we're just using USB 2.0, we're not using any fancy power negotiations. We want to have a 5.1K pull-down resistor on both of these, and that simply tells the upstream device, in our case, typically a computer, that just supply us 5 volts, nothing fancy. We will limit our current consumption to the 500 milliamp limit. That's all that does. And now for the D minus and D plus, it's good to have some ESD protection on it. And for this, I've also done some videos on choosing these, but the TLDR is basically the faster the interface, the lower the capacitance of whatever protection you are using, and that also means the worse it'll be protected. So this ESD diode is specifically designed for USB interfaces. It's a really small part. It's an SOT723, which is kind of in the same range as the 0402s. Since this is a 2.0 interface, this is designed for USB high speed and USB 3.0. It could be a beefier protection, but since we're doing a small board, I figured just keep with that same theme. And now all of these we are not going to be using because, like I mentioned, this is all for the other features of USB-C, which we don't need. So the USB side is done. Shield is left floating. Grounds are connected. The 3.0 and above features are not used. The USB D minus and D plus are connected to the corresponding D minus and D plus of the microcontroller. We have an ESD diode to protect the interface on the microcontroller. The CC1 and 2 pins are pulled down to ground with a 5.1K resistor to help with power negotiations. And then our input supply drops down from 5 volts to 3.3 volts and then feeds our microcontroller. So now from here, the next place that makes the most sense is to do the flash chip, which is pretty straightforward. I am using one of these specifically like approved parts by Raspberry Pi. So it should make it quite a bit easier to do the routing for it or the configuration on the software side. And for this, I'm using the alternative pin assignments, which is pretty cool. since this is going to be used in QSPI mode instead of just standard SPI, I need to adjust these so it's IO through IO 0 to IO 3 and flip this. And since we have the resistors in here, we don't have to worry about anything on this side, and we can just tie them directly across. So 0 to 0, 1 to 1, and so on and so forth. And now, since this would be a really annoying route to go over to here, what I will do is just label these. So QSPI SSN, and then copy paste this, and then change this to clock. Oh, actually, S clock to be fancy. So now we move clock to here, and then chip select to this. And then kind of a gotcha with the chip select sometimes is you have to make sure it's held in a known state. You can do that in software, but since this is all pretty well configured with the Pi itself, it's still good to have a pull-up. And this was something I had seen in the past in the data sheet or one of the app notes, that depending on the RAM chip you use, this can be populated or not. So this potentially will be a do not populate a DNP, but for now we'll just keep it like that. And now throw on our 3v3. So power comes in, gives us our QSPI or quad bidirectional connections, our chip select, and then our clock. And then, of course, we cannot forget our decoupling cap and connect it to ground. Okay, so now from here, this is something that if you're following or doing this, you probably don't need, because you can just use the USB programming interface. But it's also nice to just have the direct I2 or the direct SPI to the clock and IO that it uses internally. So for here, again, just take the net names, name this SWDIO, and then I will throw these. I'll throw the IO on the one that I typically use for IO. Clock goes here, and then I will take the reset, and these don't need to be that long. And this is not used, so I'll throw a do not connect flag. And then for power, something that I like to do with most of these interfaces is not connect it straight to ground, just in case there's a surge or something else like that, since it's just going to be used to detect voltage. Even if that, it actually probably won't be used at all. I throw on just reusing one of our 27 ohm resistors, and this is another kind of the common theme, is something you certainly don't need to have most cases, but it's nice to have sometimes. So move the tag connect there. So now pretty much all we have left on this side is to do the GPIOs, which I will first slide these up a little bit. And now for this first connector, what I'm going to use is just a standard 2.54 millimeter pitch connector, and in a 0 by 14 or 1 by 14 rather. And let's rotate this over. And for this connector, I want it to have power on it in addition to having all of our connections. So I'll just copy paste all of these over. And now pin 3 I will use for ground. Pin 2 I will use for 3v3, and then pin 1 I will use for 5 volts. And now since we're running out of room up there, I'll just slide this down, and then we can drag these to be even and slide this over. So now our first header is good to go. It has all of our IO and then a few power connectors. And now for the other header, it's going to be a 1 by 16, so it's going to have 2 extra pins. And the connection for this will be pretty similar to what we have already done. And then something you've probably already seen me do is I copy and paste these quite a bit, just because I find it's the easiest way to keep all the lengths consistent. And now actually move this down, give us a ground here. And for these three, what I am going to do is throw on both the reset and the other programming connection. So if you don't want to use a tag connect, or if you want to use these for some other use, they're at least on this also. Because what I'm thinking is it's probably useful to have as many interfaces on these headers as possible. So if you don't want to use that tag connect, or you want to use for something else, it gives you that ability too. So there's all of these connectors done. And now, how I had said before, we need to use the GPIO 14 and 15 for the I2C interface. We will work on that now. So for this, the connector, which again is the standard with Adafruit, is this SM04B. And I think it's made by JST. Go figure. So let me flip this. And the pinout for this, again, is just based on what they use. So I will just copy that directly from them. So pin 1, we drop to ground. Pin 2 is 3v3. And the one thing that I thought was a little weird is like some of these work with both logic levels, some don't. So if you're going to use this with one of their sensors, make sure that you're powering the sensor, not externally, so it doesn't apply 5 volts to any of the pins, which would obviously not be good for the microcontroller. So this will label as GPIO 14, this will label as GPIO 15, and for this, we throw GPIO 14 on pin 4 and 15 on pin 3. And now I will also go ahead and throw on the same ESD diode that I used for the USB here. And if you're doing this actually for like maximum protection, you would definitely want to use a better TVS diode. When I say better, I mean better protection, because these are way lower speeds. So you can get away with a higher capacitance TVS diode. But for this, I don't really care, and I'd rather keep the bomb count a little bit lower. Now next, we need to have a couple of switches on the board just to make throwing it into boot mode and to reset the board a little bit easier. So I will do 2 switches, and then another thing that I do, just a little protection, because these could have a ESD event on them. You could throw an ESD diode on them, which certainly wouldn't help. But what I also like to do in this case, what I'll only be doing is throw a 1K resistor, which again, check out my ESD video where I did a bunch of simulations and showed how well different protection schemes work. And for these, we will need to use chip select and then reset. So by pulling the chip select for the QSPI low when it is booting, what this does is it will put it into a state to where you can then load it with like on the device manager, it shows as a mass storage device for USB, and then the reset simply just resets the board. Now let's throw in the RGB LED, which of course this is just for indication, and you can use it as just like a sanity check to make sure everything is working. And for this, we need to use the 5-volt rail, which is kind of annoying because now we have to have 5 volts for more than just that. But for true RGB, it's kind of hard to get away without having that, which not 5.1K. This needs to be 510.0402. Okay, and now to control these, we will use just a standard logic level N-channel FET. Another thing I like to do is throw on a resistor since obviously we're not going to be doing anything high speed here. And then for the 0, 1, 2, 3, we will take this as LED R. We throw them here like that. And now, unless I made some stupid mistake, which is very likely, we should be able to go ahead, annotate it, and do an ERC. And 6 and 7, which, like I had mentioned, these are just going to be non-connects. And we could, of course, have them be non-connects on the internal sheet, but it doesn't matter. Both ground and 3v3, well, that should not be the case because we have that. I'm sure people have been watching this video thinking about that this whole time. That is what we use an ERC for, though. So that pretty much wraps up the schematic. I'll go ahead and kind of clean everything up just because I did this obviously on the fly, and if I did make any mistakes, I'll clean those up. But otherwise, the next video will be going through the PCB and laying out the board, and then the third and presumably final video of this series will be assembling and then testing this board. So I hope you guys enjoyed this video. I hope you enjoyed this format. Let me know in the comments, and I will see you guys in the next one.